All right, so we're still in section 6.1. We're still talking about the law of sines. And before we go on to the ambiguous case, I wanted to sketch out really quickly why the law of sines works the way it does. So just really quickly, I want to go over how we come up with these formulas. So if I draw a triangle, we're going to say why it works. If I draw our triangle, we're looking at some oblique triangle. And we said that we've been labeling these A, B, and C. And what we're going to do is draw the altitude of this triangle. So I'm going to draw in a dotted line here for the altitude. And this makes a 90-degree angle here. And we're going to call the altitude, the length of the altitude, h. And if we calculate we want to figure out how to find the length, or find the length of h, find the value of h. So we know angle A. Let's say we know angle A, we know angle B. So we want to find the altitude. So from this triangle here on the left, we can say that h, because this is a right triangle, we can say that h equals B sine A. We're using this right triangle. H equals B sine A. Now if we look at the right triangle here on the right, this tells us that H equals A sine B. It's the same length, we're just using two different triangles to calculate it. Because these are both expressions for h, we can set them equal to each other. So b sine A equals a sine b. If I divide both sides by sine A and both sides by sine B, I get b over sine B equals a over sine A. So there's one of our relationships from the law of sines. If I drew a different altitude for the triangle, I could do the same thing for the other relationships that we have with the law of sines. So this is why the law of sines looks the way it does, and this is why the law of sines why it turns out that all these relationships are true. So I just wanted to point this out because the altitude here, the length of h, is going to come into play today with what we do. So we're going to talk about the ambiguous case, and then we're going to come up with some formulas for the area of triangles using sines. So what I want to do first is, in your book, on page 412 and 413, there are a bunch of diagrams that list out some possibilities for triangles. So if you have a book, open up your book. If you don't have a book, get with somebody who does have a book so you can look at these, because I don't want to draw them all out. There are a bunch of possibilities on the top of page 412 there. It lists possibilities for triangles, how your triangle could be configured. Now, as a reminder, what we did yesterday, we were always given, the combinations that we were given for our triangles yesterday were either angle, angle, side, or angle, side, angle for our triangle. We were given one of those two combinations. When we're given these two combinations, we can always find the third angle. There's only one possible value for that third angle, because the angles in a triangle always have to add up to add up to 180. So if we have these two possibilities, the law of sines will always just give us one triangle that works. The ambiguous case comes into play when we have side-side angle combination. And if you remember back from geometry, we could use angle side angle or angle angle side to prove that triangles were congruent. Those were two of the postulates that we could use to prove that triangles were congruent. But SSA, side-side angle, was not a postulate we could use to prove triangles congruent because we didn't necessarily get a congruent triangle. And that's what the pictures on page 412 are telling us. We can, if we have a side-side angle combination, we could have no triangles, no possible triangles. We could have one possible triangle. Or we possibly could have a case where we have two triangles. Two triangles that have the same combination of sides and angle. So we have three possibilities when we have the side-side angle combination. So when we're working with the side-side angle combination, it's really important to draw a sketch so you have an idea of what your triangles look like, and then we'll talk about how we decide if we have one triangle, no triangles, one triangle, or two possible triangles. So no possible triangle is when we have a situation like this, and this side is really short, and we know this angle. And side A, no matter what this angle is between side A and side B, it doesn't matter how I move this little side around, it will never connect with this third side of the triangle if we're given this angle. If we know this angle, no matter what I do with this little side, it will not connect with the third side. So this is how we could have no possible triangles with a side-side angle combination. And when this happens is if I draw in my height, A is smaller than the height. The length of A is smaller than the height of this triangle. So no matter what I do, A is not going to connect. One possible triangle is the case that we've been looking at. The triangle looks like the ones we've been looking at so far. So this is angle A, and this is side B, and this is side A. So this is our one possible triangle, and this is, if this is my height, if A is bigger than B, and A is bigger than the height, we have one possible triangle. Now the two possible triangles come into play. That case is when we have triangles. I'm going to switch pages here. When our triangles look like, I'm going to draw these triangles a little nicer. A is bigger than B, and A is bigger than H also. And we'll look at, yes. I'm going to talk about the case when A is not bigger than B for the next one. Okay? So here A is less than B and A is less than H also. Then they won't connect. So Cedric asked, why does A have to be bigger than B? I'll talk about the case when A is smaller than B for the next case when we have two possible triangles. So our triangles are going to, our triangle could look something like this. And I'm going to draw in my altitude here. My height is here. And what I could do with this triangle is I could swing. Let me label my sides. This is A, this is B, and this is C. I could swing this side around in an arc, and it could also connect right here. So I could have a different triangle with the same two sides and the same angle, but my other triangle could look like this. And this is still length A, same as this length. I just swung that side around in a circle so it connected over here. So I could have this bigger triangle or this smaller triangle. And that's when we get the ambiguous case. And that gives us two possibilities for the size of angle B, because I can have this angle or I can have this angle. And I have two possibilities for the size of angle C. I can have the bigger angle or I can have the smaller angle. So I have two possible triangles. And this is when A is smaller than B, but A is still bigger than the height. So A is smaller than B, but A is still bigger than the altitude. The length of A is longer than the altitude. And that's when we get two possible triangles from the law of sines with the side-side angle combination. And our possibilities for angle B, we have two possibilities for angle B. And the two possibilities for angle B are supplementary. So we come up with two possible values for angle B, and those two possible values are supplementary. And the reason that is if we think back to our unit circle, and we have our unit circle here. If I have an angle here, the sine of the angle is the y component. I can have an angle over here that has the same y component. And these two angles, this angle and the bigger angle, add up to 180. They're supplementary. So those are my two possible angles for angle B, and they're going to be supplementary. So we're going to look at an example of each of these three possibilities, each of the three cases: no triangle possible, one triangle possible, and two triangles possible, to look at how that works out. And remember, this comes up when we're working with the side-side angle combination. Side-side angle combination, when we're given two sides and an angle, we have these cases that could come up. Any questions before we go on to the examples? So remember, angle side angle, when we have two angles in a side, angle side angle or angle angle side, the law of sines is always going to give us one triangle. When we have side side angle, that's when we have to be careful about the different cases that we would have. So let's look at some examples. Let's say that we have A equals 26 degrees. Side B is 5. And side A is 21. We want to find the other sides and the other angles. So we have two sides and an angle. We have the SSA combination. This is SSA. So we have to make sure that we have either one triangle, no triangle, or two triangles. So let's make a quick sketch and look at what we have. So I'm going to draw my triangle like so. And we don't know for sure whether we have a triangle, but we'll take a look. I'm going to say this is A, angle A, and this is 26 degrees. And this side is 21. I'm going to call this angle B and this angle C, and side B is 5. So the problem tells us that, gives us these two sides, this angle. So let's make sure that this triangle is going to work. We know that this side is bigger. Side A is bigger than side C. Let's make sure it's bigger than the height of the triangle also. So let's calculate the height. If we calculate the height is 5 times the sine of 26 degrees. What's the biggest value for the sine of any angle? What is it? Josh says 1. The sine is always going to be between 0 and 1. So the height, if this number is between 0 and 1, the sine of 26 is between 0 and 1, the biggest that this height could be is 5. So we know that this is less than 5. And 21 is bigger than 5. So 21 is bigger than my height. So we're going to have one triangle. So now we're going to use the law of sines to figure out the rest of the sides and angles for my triangle. So I'm going to say that I'm going to solve for angle B first. So I'm going to say that the sine of B over 5 equals the sine of 26 degrees over 21. So I'm using side A, angle A, side B, and angle B. And so this tells us that sine B, sine of angle B, is 5 sine 26 degrees divided by 21. And if we plug that into our calculator, we get sine B is about 1.044. And if we have the sine of the angle, how do we find the angle from there? What is it? Inverse sine. So B, angle B, is the inverse sine of 1.044. And we get that our angle B comes out to be about 5.99 degrees. So angle B comes out to 5.99 degrees. We can plug this in to, we can put this into our triangle. Once we have angle B, yes? What is it? Oh, point, right, because it has to be less than 1, right? So our angle comes to 5.99. I've got this angle. Once I have angle B, figure out angle C because all of the angles in our triangle have to add up to 180. And then I can use the law of sines again to find side C. So I can find the rest of the sides and the rest of the angles once I figure out this angle. Does that make sense? And we knew we had one triangle because this length was bigger than this length. Side A was bigger than side B, and they're both greater than the height. So we get one triangle. So I'm not going to go through doing the law of sines again. This is like the problems we did last night. We have one angle, we can figure out the third angle, and then we can figure out the third side. All right, let's look at another example. We good to move on? Anybody have questions on that one? All right, let's look at our second example. For this one, we're given that angle B equals 78 degrees. Side C is 12, and side B is 5. We want to find angle C. So let's sketch out a triangle. I'm going to draw my triangle to look like this, and I'm going to call this angle B this time, just to make it easier to work with. And I'm going to call this angle C and this angle A. So side B is 5, the side is 5, and side C is 12. And we need to figure out if this is going to give us one triangle, 0 triangles, or 2 triangles. We have a side-side angle combination, so we have to be careful. So right off the bat, we can see that side B is smaller than side C. If side B is smaller than the height of the triangle, if I draw in my altitude here, if 5 is smaller than the height, then we cannot make a triangle. We would have a triangle that looked like this. And no matter what we do here, this won't connect. So if 5 is less than the height, we won't have a triangle. So let's calculate our height. Our height is 12 sine 78 degrees. And this gives us, if we plug this into our calculator, we get about 11.7. And 5 is less than 11.7. So no matter what we do, this side won't connect with this side. So I'm going to erase this and make a dotted line here because we wanted to see if it would work. So it won't connect. So this is not, there's no triangle possible. No matter what we do with this side, it's not going to connect down here if we have this angle and these two sides. No matter what we do, it won't connect. And what would happen if you plug these numbers into the law of sines, you would get something like the sine of C is 1 point something. You'd get something bigger than 1, and you plug that in your calculator and you get an error. So if you try to use the law of sines on this one, you'd get an error. And that would also tell you that you don't have, there are no triangle possible. So there's 2 ways you could look at it. I think it's good to be able to visualize what your triangle would look like in this situation. Yes, you would get an error. Any questions on that possibility? All right, let's look at our final case when we have 2 triangles. We have A equals 29 degrees. Side A is 6 and side B is 10. We want to find angle B. So we're just looking for one additional angle here. So let's sketch out our triangle. Now we don't know exactly what it looks like, but we want to just get an idea of how we're going to use the law of sines here. This angle is 29 degrees. This side is, we'll call this angle B and this angle C. This side is 6. This side is 10. And we have a side-side angle combination, so we have to be careful because we could have different possibilities for our triangle. So this is like the last one in that side A is less than side B. So we need to see how it compares to the height to decide if we have no triangle or two possible triangles. So I'm going to sketch this in here, my altitude, and its length is h. So let's calculate h. H is going to be 10 times the sine of 29 degrees. If we plug that into our calculator, we get about 4.85. So this side is smaller, side A is smaller than side B, but it's still bigger than the height. So this is the case where our triangle could look like this, or we could swing this around and our triangle could look like this. So we have two possibilities for this triangle. That's what this tells us, because side A is smaller than side B, but it's still bigger than the height. We could swing that side around. So let's calculate, let's use law of sines. We know we get two possible triangles. So angle B can have two possible values. We can have two possible values for angle B. So we'll calculate, we'll figure out both of them. So let's use the law of sines. I'm going to say,
Wait, so how do you know, like, if it's this one and not the first one?
on the very first one we did, this side was bigger, was longer than this side. So that was our first one. If we have no triangles or two triangles possible, that second side is going to be shorter than the first side, and we have to figure out how that compares to the height of the triangle. So let's do our law of sines. I'm going to calculate. We want to figure out sine B over 10 equals the sine of 29 degrees over 6. So sine B is 10 sine 29 degrees over 6. And we plug that into our calculator, we get sine B is finally we get from this, we want to take the inverse sine. So B is the inverse sine of whatever we get in this calculation. 10 sine 29 degrees over 6. If we plug that all into our calculator, we get about 53.9 degrees. And our second possible value for angle B is going to be supplementary to 53.9. So we take 180 and we subtract 53.9 degrees, and we get 126.1 degrees. So when we have the two triangle possibility, our two possible angles are supplementary. We can find one angle using law of sines, find the second angle by subtracting from 180. And then we can, if we wanted to find the other sides and angles, we would have to use the law of sines for both of those possible angle B's. We would have to use it for both because we could get two different values for angle C. And we get two possible lengths for side C also. We get the longer one here, or the shorter one here. So we'd have to find two possible values for side C and two possible values for angle C as well. So that if we're finding everything we want, all the information that we might need to look for, we'd have to do a little more work with this situation. Yes. How did we decide it was two triangles? All right. So what we did was, first off, we saw that side A was shorter than side B. So that tells us immediately that we would either have, if this side is shorter than this side, we either have zero triangles. We would either have a case that looks like this, where this side is too short to connect, or we're going to have the possibility where the side's long enough and we can swing it around and connect it in two places. What tells us which situation we have is how this side compares to the height of the triangle. If this side is shorter than the height of the triangle, then we have a situation like this. If it's longer than the height of the triangle, then we have a situation where we could swing it and connect it in two places. So we calculated the height. The height was 4.85. 6 is longer than 4.85. That tells us that we would be able to connect that side in two different places. Okay? All right. Any questions? One more really quick thing, and then we'll be done for today. We can use the sine of an angle in a triangle to come up with an area formula for triangles. So that's the last thing we're going to talk about today, is area of oblique triangles. So let's draw a triangle, and we will come up with an area formula that involves the sine of one of the angles. So here's my oblique triangle, and we have A, B, C, and the sides A, B, and C. And I'm going to draw in my altitude. So the area of this triangle, how do we find the area of a triangle? Base times height divided by 2, 1/2 base times height. So the area is 1/2 base times height, or base times height divided by 2. So for this triangle, what is the way I drew the altitude in here? What would be the base of this triangle? What length? C. C would be the length, the base of the triangle. So our area is going to be 1/2 C. And what is our height? Our height is h, and we can calculate h because we know the value of angle A. What have we been doing with all of our ambiguous cases? H is sine A times B. Perfect. B times the sine of A. So I'm going to plug that in here. So our area equals 1/2 BC sine A. So if we know two sides and an included angle, we can find the area of our triangle. We can do the same thing with the other sides and the other angles if we draw our height in from the different angles, and we can come up with 3 area formulas for an oblique triangle. So we have 3 area formulas. Area equals 1/2, the one that we worked on, BC sine A. It's 1/2 AC sine B. Or 1/2, which combination don't we have? AB sine C. So if we have two sides and the angle between them, we can calculate the area of our triangle using one of these 3 formulas. So this is a nice shortcut for finding the area of an oblique triangle. And this one it's pretty easy to work with these. We just need to figure out which parts we have and plug in our numbers. So I'm not going to do an example of these. These are pretty easy. We just need our 2 sides and an angle, and we can find our area. Any questions? All right. Homework for today.
Can you leave that up for me?
Sure.
Or just write the memo down there.
Yeah, I'll just scroll down here. There you go.